Hi, today I'm going to be talking about polar areas, 9-3. Today I'm recording on Pi Day. Ooh. So we're going to make a offering, a prayer to the gods of mathematics, that this lesson is shorter to record, shorter to watch. If you haven't seen 9-3, it's about 2 hours long. Sorry, 9-2. It's about 2 hours long. It tells you over all of polar's basics, including the beginnings of polar calculus, like polar tangent lines. So if you haven't seen that, it's really necessary before you watch this. For instance, if you look at this curve and have no idea what does that look like, that's not going to be happy making going forward. Petal. It's a rose petal curve. It's a rose petal where the roses are length 3, the petals are length 3. N is odd, so there's 3 of them. You know what? Let me try it this way. I've had some trouble sketching this, so it looks approximately right. Setting up those points really helped me. That was the first try. Well, it was the first of like 5 that you didn't see because I recorded over and over again. Alright, here's the rose petal curve. Now, if I asked you where do I start on this rose, what would you do? You should think about plugging in 0, but most people just intuitively think you start at the pole. That's not true. Okay? What really happens is when I plug in theta equals 0, I get cosine of 0, which is 1, and r is 3. So the coordinate 3, 0, where that's an r and that's a theta, FYI, don't get confused, is right here. So I'm starting here. And as theta increases, my radius is going to get positive, positive, positive until it gets to 0. Okay? So we're really going to trace out this top branch of the petal. Now that's going to be really important for us to understand. That's why Mr. Nathan Stearns does not like this unit. So we're going to get half of a petal this way. That's going to be a really important insight. Let's see at what time it hits that value. I'm going to set up the equation 3 cosine 3 theta equals 0. Cosine 3 theta equals 0. We're sort of wondering when is the first time cosine will hit 0. Cosine will hit 0 for the first time at pi over 2, the first positive theta, I guess I should have said. And so theta would be pi over 6. So we're saying this is that green coordinate. It'll hit the pole at theta pi over 6. So what I'm going to be able to compute using this integral is the area here between sort of like this. I'll become clear in a minute. I like to draw these spokes. So, unlike rectangular coordinates, our area representative rectangles are spinning out radially from the pole. From the pole. Okay? So, here I go. Wait, are they spinning out radially from here? Possibly. That's the same basic idea, symmetry, but yeah, I'm going to say it doesn't matter. Okay. So my area of that pink part would be 1/2, using this formula, from theta equals 0, drop the pen, from theta equals 0 to theta equals pi over 6, r squared So notice the pink region represents 1/2 of the petal. So the real area, I'm not sure how big of a fan I am of this, is going to be 2 times all of that. Because that would get me this side of it. Oh wow, I can't draw. Okay, and that's just in case we're going the other way. And if you type that in your calculator, which I will trust you all to do, we get this number, accurate to 3 decimal places. Does that make sense? So, what sort of things am I adding up? What I'm adding up is sort of the area of a circular sweep here. This should remind you, in some way, shape, or form, of our area of a sector, a circular sector, which is theta divided by 2 pi how much of the circle you have times pi r squared. Now the problem is the last time you saw this formula you used angles in degrees, so you may have said angled over 360, but obviously with radians, this is one of the reasons we use radians, this formula becomes all the more pretty. So that's the area of a circular sector, so we're adding up infinitely thin circular sectors that have an angle, not a whole theta, but a d theta. And that's in general how we're going to do it. Almost every time with polar, you're going to have to do this. Because the way polar curves work, where they go this way, that way, every way, is that they'll intersect themselves. And our integral formulas won't be able to handle that intersection. So you want to make sure you set up this equation to find the bounds of the integral in every case. Someone's coming. Just someone coming to take a retest. So here we go. Frequently, because of how curves intersect themselves, we'll have to have that doubling factor, because our integral formulas cannot handle curves which intersect themselves. Okay, so let's talk about how to find intersections. Finding the points of intersections of these two graphs, just like in rectangular coordinates, it's often as simple as setting them equal to each other. So if I want to find all the places where r equals 1, I just plug in r equals 1. So 1 equals 1 minus 2 cosine theta. Negative 2 cosine theta equals 0. Cosine theta equals 0. Theta will be like pi over 2 and 3 pi over 2. Now the problem with polar coordinates is that this is misleading in a major way. So they'll mention of the graphs, but you always need to be careful to draw the graphs. So I'm actually going to graph this one in blue. 1 minus 2 cosine theta. Does anybody know what that is? It's a limison. So in fact it's a limison that looks like, well, when theta equals 0, we're getting negative 1. When theta equals pi over 2, we get 1 for 3 pi over 2. And when theta equals pi, we get all the way out to negative 3. So it's a loopy looking limison. like that egg-shaped guy. We'll leave it like that. And r equals 1, you all need to know what that looks like, is a unit circle with radius 1. We know that was redundant. You should all know it's redundant too. Now, we have these two intersections right here and here, but we also have one comma pi and negative 1 comma 0. I'm sorry, that should be an or. It's the same point. So why do our equations miss that? Why do our equations miss that idea? It's very strange. And the main kind of reason for it is that when theta equals 0, r is going to be recorded as negative 1. And this r will never look like negative 1. So one solution people proposed last year is always thinking of this as plus or minus. And that would have found you these other solutions. If you said r equal negative 1, you would get cosine theta equals 1. And that would be pi. But that's hard. So always be careful for that. What I'm saying is, okay, if we thought, let me write it down for you visual people, r equals negative 1. And that's this point right here. Because that is, it's all in the circle. R equals negative 1 is the same circle. Is equivalent to r equals 1 in polar. Negative 1 equals 1 minus 2 cos theta. Negative 2 equals negative 2 cos theta. Cos theta equals pi. Or sorry, cos theta equals 1. Theta equals pi. Okay? That's the algebraic way to do it. There's a graphical way to do it too, but it requires you to know, and Leven has an inner loop and everything. Okay. Area between two curves. Now, if rectangular is any key, this is going to be a little more complicated than just the area of one curve. So the first thing we're going to do is draw the graphs. So what does r equals negative 6 cosine theta look like? R equals negative 6 cosine theta is a circle with radius negative 6. Okay? And that means radius positive 6. Sorry, diameter negative 6. I'm so sorry. So that means it's going to be here to here. Fine, I'll do it again. Notice that the axes seem stretched out. 2 here is not 2 here. So it is going to look oval shaped. I'm not going to just misdraw it. Although I'm sure this drawing is not really perfect. That's supposed to be a circle with weird scale. Okay? That's this guy. And again, this guy over here is a limison. And again, for limisons, I just graph 4 key points. Theta equals 0. I get 0. Pi over 2. I get 2. 3 pi over 2. I get 2. But polar coordinates 3 pi over 2, out 2. And then pi, I would get 4. No inner loop. Just this ugly looking guy. Alright. So now you have to focus on the language here. The region common to these two. And that's going to be a weird question to ask frequently. But this is not common, this is not common, and this is not common. And it's sort of where do they both exist at once. And in this case, it is going to be sort of this inner region here. Now, this inner region is fairly hard to talk about. This inner region will mostly be the pole touching red. And I'm going to draw that in orange and hope it stands out. I'm going to draw it in light blue. Pole to red. So here's what's happening. This sweep, this spoke, 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 spoke. And here's why Nathan hated it, everybody. The pole to green. Sorry, green. There's going to be a pink region here where what we're touching, if we're going out from, is not going to be bounded by the red curve. It's going to have to be bounded by the green curve to come back to the pole. And this is why it's hard to imagine using polar coordinates, and with bad drawings especially. But the idea is, to get back to the origin, I'm going to have to follow the green guy for a little while. Okay? So the first thing we need to do, just like in rectangular, is to find the intersections. It's not necessarily going to be bounds anymore. Okay. 2 minus 2 cos theta equals negative 6 cos theta. And usually it's not going to be that bad to solve. 4 cos theta equals 2. Negative 2? Oh, sorry, yeah, negative 4 cosine theta equals 2. Cosine theta equals negative 1/2. Theta, you want to use positive angles usually, so we can think about it nice. Okay? We're going to have 2 pi over 3. And 4 pi over 3. Okay. So, let's try to think about what's going on here. So, where's, the blue region. So that's this point and this point, sorry. The two intersections are in black. So the blue region will be the rotation from pi till 2 pi over 3. Sorry, counterclockwise. From 2 pi over 3 until pi. The blue region is from 2 pi over 3 until pi. Let's do that first. That's going to be a little easier to think about. So my blue region, I'm going to try to shrink just this. Is that possible? Okay, cool. Just grab the underlines. That's fine. So my light blue, the one that goes from pi to 2 pi over 3 or 2 pi over 3 to pi, basically we're going to have two integrals. We'll have to add the blue area to the pink area. And I know that picture is ugly. So area equals the blue. Now there's going to be a symmetric half down here, right? A perfectly symmetric half. So again, it's going to be 2 times 1/2, and now I'm going to use the formula. It's going to start at 2 pi over 3. It's going to end at pi. And again, there's a huge desire for people to go all the way around town. That's not right. I mean, you can. But it's a little nicer to write it like this. Trust me. You don't want to have to worry too much. You just want to do half. It's more complicated and you need to be good at that skill. And then, since we're using the red bound, I'm going to use 2 minus 2 cosine theta squared d theta. Now again, as always, a lot of students want to use minus here because they're used to rectangular coordinates and washers and shells and whatever, but it's not minus, it's plus. I'm adding this pink to the blue. So now we're going to calculate the pink area. Now the pink area is bounded from 2 pi over 3. It's certainly going to be part of it. And let's find out what the pole is for this guy. So this guy would be at its pole, because we're dealing with cosine, at pi over 2. So this would be a rotation from pi over 2 until 2 pi over 3. I'll write it down up here in green. At pole. And theta equals pi over 2. And indeed, when theta equals 3 pi over 2. This guy's just spinning around very quickly, right? So we're going to use this one. And now I'm pink. And I'm adding this area again. And there's going to be a similar one down here, which is maybe easier to see. Okay, that's what we're talking about. So 2, because there's 2 of them, 1/2 from pi over 2 until 2 pi over 3. See, that kind of completes that one. And because this is the green boundary, -6 cosine theta, quantity squared. And if you compute this in your calculator, I promise you, you will get 15.708. One more problem. Find the area between the loops of r equals 2, blah, 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 blah. So the area between the loops. So first, let's draw this. You should know that this is a limacon. Okay. Now, when theta equals 0, sine is 0, so we're at 2. I know it's going to be symmetric about the y. So if theta is pi, we're also going to get 2. If theta is pi, that's why I'm over here. When theta is pi over 2, we get 6. It's a big top. If theta equals 3 pi over 2, we get -2. So 3 pi over 2 rotation, -2 back. So when you see that shape, you should be very suspicious of the, it's an inner loop, right? When this number is bigger than that number, there's an inner loop. And I always draw it going through the pole. I'm not sure it's going to hit the pole, but, so it looks something like this. Kind of like a spade. Okay. I don't know why I said spade. So the area between the loops. I want the area between the loops here. So let's worry about whether we hit the pole. Because or whether it will intersect itself, right? I'm pretty sure it intersects the pole. Like, let's say that's the pole. Let's try to find out where that is. So that's 2 plus 4 sine theta equals 0. 4 sine theta equals 0. Oh, sorry, equals negative 2. Oh, look, it's the same number. So sine theta equals negative 1/2. There's two angles. What are those two angles? It should be 7 pi over 6 and 11 pi over 6. Both of the third quadrant and the fourth quadrant angle. Okay, so the idea this time is to sort of figure out all of the, I don't know, what color to use. Black. And again, I'm only going to focus on half of it. So as theta goes from pi over 2 to 7 pi over 6, let's focus on that really quick. As pi over 2, we said we were here. Oh, that was a bad idea. I'd be getting these spokes. So 7 pi over 6 for this guy, we know we're getting towards 0. But you may have noticed that we went through here. But now I'm back at the pole at least. So I'd have all of this area. And now what do I want to get rid of? Well, as we go from 7 pi over 6 to 3 pi over 2, where am I? So I'm definitely going to start at the pole here. Seven pi over 6 to 3 pi over 2. I don't know. Let's think about 5 pi over 4. Yeah, that's in there. 5 pi over 4 in here. Well, that would give me something like negative root 2 over 2. So 1 minus root 2. And 2. I think, if I'm right, it's going to be like we're subtracting, no, not that far anymore. This side of it. So we color it in. So we have all that. Okay. And I want to remove that because the area between loops would be this area. So this is symmetric over here. I'm just coloring over here because it was not filled in. So again, we're going to compute the pink. And we said these bounds, this was, sorry, that was 6 comma pi over 2. Got myself. That was 0 comma 7 pi over 6. That's the first time we hit it. And we know we want all the action up until we get to this point, which was 3 pi over 2. Let's use purple there. That's negative 2, obviously. Comma 3 pi over 2. So the basic idea will be to take the pink area which again only represents half of the area I wanted. And it goes from pi over 2 until 7 pi over 6. It's r squared, always. that would be the pink, which would have included this little inner loop. And then I'm going to subtract the inner loop, which will be 2 times 1/2. And this statement is subtract. It really is going to be subtract here because they want an area between loops. When they want common area, it's usually plus. I'm just going to go over that again. When they want common area, it's usually plus. Not saying always. And when between, it's usually minus. So now we're going to integrate from 7 pi over 6 until 3 pi over 2, so that'll get us halfway around the loop. That same exact function. And that's it. And I swear if you compute it correctly, you enter in the calculator correctly, 3.351. So that's it. That's polar area. It's not as fun as what we'll do next, which is polar arc length. Oh no, now that's the end of polar. That's polar arc length's not that bad at all. Make sure you're doing assignments 9.2, 9.3. Very important to understand polar at its full extension. If you're not doing the assignments, you will fail the AP test. I guarantee it. If you are doing the assignments, thank you for your hard work. I appreciate you guys doing math in your spare time. I'll talk to you soon. Goodbye.